Hello and welcome to our second MRI physics video. Today we'll be discussing spatial specificity, which sounds complicated but is just where are we scanning, or where are we receiving MRI signals from in the brain. So I'll explain this question in the next slide. Okay, so let's quickly recap the basic physics that we discussed last time. Inside the body, protons behave like little magnets. When we put a patient in the MRI scanner, the big main magnet, or the static magnetic field, makes these protons precess. That just means that they spin around in a particular way because of that magnetic field. If we want to push a proton out of alignment, we hit it with a radio frequency pulse. That radio frequency pulse gives the proton energy, so we say that it's excited. When it's excited, it tips away from the main field. And once we switch off the radio frequency pulse, the proton relaxes back to its original position. So that's called relaxation. As it relaxes, it gives off a signal. The way that it relaxes depends on the type of tissue that it's going through, and that is what gives us the contrast in MRI. So contrast, which is how we see different tissues. See different tissue. The new question now is, if we know what tissue we're looking at from relaxation, we still don't know where in the brain that tissue is. How do we know where the signal is coming from? To answer that, we need to talk about the Larmor frequency. So the proton only responds efficiently to a radio frequency pulse if we hit it at exactly the right frequency. This frequency is called the Larmor frequency. Consider it a kind of measure of the radio frequency pulse. A good way to think about the Larmor frequency is a person on a swing. If you push them at random times with random strengths, nothing much is going to happen because they might be pushing against you, or you might not be pushing hard enough. But if you push in sync with the swing, you transfer energy very efficiently and they will swing higher. So with this image here, if this individual is swinging from here to here, if we push at the right moment while they're going in this direction, and we push exactly at here, for example, with the right amount of force, the next time they swing up, they're going to swing a little higher. And then let's say they come back again, and then you push them here again. The next time they're going to go even higher. And it's the same idea here. If we use a radio frequency pulse at the Larmor frequency, we knock the proton out of alignment in the most efficient way. The Larmor frequency has a formula, and I'll show you that in the next slide. It is that the gyromagnetic ratio is multiplied by the magnetic field. The gyromagnetic ratio is a constant for the proton. Gyromagnetic ratio is a constant for the proton, depending on the tissue. of course. So what we consider here is changing the magnetic field. If we change the magnetic field, the Larmor frequency will change as well. So all we need in an MRI machine to figure out where the signal is coming from is another magnetic field that changes across space in a way that we already know. To do this, we use something called gradients. Gradients are small magnetic fields that are added on top of the main field, and they increase linearly across space. What that means is that we know that they get stronger or weaker in a particular direction. We have three of them, a GX, GY, and GZ, which are just, from left to right, from front to back, and from head to foot. So as an example of this linear gradient, we might say, for example, that the top of the brain will have a different magnetic field strength to the bottom of the brain. So it might be stronger at the top and weaker at the bottom. And so the precessions will occur at different frequencies. So the key idea, once again, is that the gradients make frequency depend on the position that you're at in the brain. So in this MRI scan, it seems like we are scrolling continuously through the brain. But this is actually a series of images or slices from the brain that we are selecting as we go through. So this probably consists of a couple of slices, and each image that you see at a particular point in time is a different slice. Okay, now let's see how we use gradients to pick a single slice. It consists of two main steps. To select a slice, we first apply a gradient in usually the Z direction, which is from head to foot. And then we send in a radio frequency pulse. Because of the gradient, each position along Z has a different Larmor frequency. We choose an RF pulse that only covers a narrow range of frequencies, which means that only the protons whose Larmor frequency falls inside that RF pulse range will be excited. In other words, only one thin slice of tissue lights up and gives a signal, and this is our selected slice. So if we want a different slice, we can either change the linear gradient or change the pulse frequency. That way, we can move the slice up or down through the brain and get the MRI scan that we saw in the previous slide. So now to pick within the slice that we've selected. So within each slice that we get, the image is made up of lots of tiny 3D blocks called voxels, which is short for volumetric pixels. Something like this. It's vertically and horizontally like that. Consider that each of these little squares is a voxel. So that's one, that's another, and that's another. We can use a very clever selection or a very clever combination of gradients to work out exactly which voxel the signal is coming from inside the slice. That's where the frequency encoding and phase encoding come in. They sound very complicated, but they're just the different gradients in the Z, X, and Y axes. So the Z, as we've discussed already, tells you which slice, and then within the slice, the X and Y tells you which column and which row voxel specifically is being referred to.